I'm Stephen Foskett, the organizer of Tech Field Day, and we're here in Austin, Texas for Tech Field Day 13. I'm joined today by Robin Systems and a group of invited delegates from around the world. They are to ask questions and participate in the discussion. If you'd like to learn more about what we're doing, go to techfieldday.com, and you can find more videos like this at youtube.com/techfieldday.
The next thing about data applications is performance, right? And the one thing that Deva talked about, right, in the last, 1.5 hours, I guess, he did Cassandra clusters, multiple of them, cloned them, Oracle cluster, cloned that, MySQL, and so on. So all of these applications are running on just these 3 boxes here, right? So which means that you're consolidating your applications. Now, when you consolidate applications, you ideally also want to control how much resources each application will get. Resources could be compute resources as well as storage resources, right? So we're going to talk about how Robin allows you to control quality of service of your applications. So the first thing is, if you remember the picture that I showed you, the architecture picture, we have presence all the way from compute till the storage. We have control over the entire I/O pipeline. So because of that entire control of the I/O pipeline, what we could do is that we allow a user who's spinning up the application to specify what is the max number of IOPS each application can get. It can be done either by the user or, of course, the admin is typically who would do that, tenant administrator. And that is so that you can throttle the maximum usage or utilization of a particular application.
Can you do that based on latency instead of IOPS?
That should be doable, again, because right now we expose it as IOPS because that's the way it is, but that's something that we can do. And again, that's purely because we have a control from top to bottom, right? So of course, then that is the max, right, which is ensuring that you're capped off at a certain number. The next thing is minimum, right? You can also specify that you want a minimum number of IOPS per application, right? So that you have it reserved, and whenever your application needs it, it is guaranteed to get that. And then the third thing is you would also like to have relative priorities for different applications. Let's say that they have the same max and min, right? And you have a gold app and a silver app and a bronze app, right? You would like to control how much each one gets using relative priorities, right? So all these 3 things can be done. And again, as I said, this can be done because of the control that we have on the top and bottom. The max is enforced on the compute side, where there's a source of where the I/O is originating, because you can cap it there. The min is enforced where the data is actually hitting the disk, because that is where you get IOs from multiple applications across the entire cluster. And that's where you need to ensure that your IO scheduler is guaranteeing the min. And priorities are enforced both at the top as well as at the bottom.
For the priorities, how granular is this? Is it just like a high, medium, low type thing, or can I go in there and actually say, like the MongoDB is 3 times as important as Postgres?
Yeah, so we allow 1 through 5.
Okay.
But there's no reason why you cannot go 1 through 10, but the more knobs you give, it becomes more complex, right? Or confusing. How do you specify? So it's 1 to 5.
Okay, thank you.
What happens when you can't achieve a minimum number of IOPS?
Yeah, so in order to get the minimum, what we do is as I said, we discover the device characteristics, right? So we basically say that this is the capacity of your disk. And in order to guarantee something, you have to do some amount of reservation, right? So let's say you have a disk that does 80,000 IOPS, and you bring up an application that requires 40,000. So we ensure that the next app that comes in can be using no more than 40,000, so that this 40,000 that you want for the first app is guaranteed,
okay.
Right? So now if you bring up an app and let's say you want 50, we'll say we cannot bring it up because it requires a minimum of 50. You don't have capacity in the infrastructure.
So you'll prevent me from being able to over allocate. So if I'm trying to allocate 100,000 IOPS to something, but my environment can't support 100,000, you'll give me that message that I can't do it?
That is correct.
Okay.
All right, so one of the things is, we talked about consolidation of apps, right? Data-heavy applications. Now, why do you want to do that, right? Number one is the machines that you get these days are a lot more powerful than they were 5 years ago, right? And whenever you talk to our customers, they basically say that they are running their data-heavy applications, whether it's Cassandra or Mongo or Hadoop or whatnot, all by itself on one bare metal machine. They don't virtualize because there's a virtualization performance penalty because of virtualization. Hypervisor has a penalty. That's why they don't virtualize. And they put this one app on this big beefy machine, which is only getting more and more powerful year over year. And what they find out is the utilization of the bare metal machine is pretty low. And what we are saying is, okay, now why don't you go consolidate your data heavy applications so you can bring up your utilization, And of course, we don't give you, there's no performance degradation. I have one more set of slides for performance, I'll talk about that. So if we are pretty much near bare metal performance, right, in terms of our IO path and so on. So now we'll allow you to consolidate without losing performance, right, and increase the utilization of your machine. However, you still have this noisy neighbor problem, right? And this noisy neighbor problem is something that the VDI market has solved, right? I mean, they have solved it either using a write-back cache or whatever it is. But it's slightly more tricky when it comes to data-heavy application. And the reason for that is when you look at simple apps, maybe something like a MySQL or a Postgres, it might write to one storage unit, one storage LUN, right? So it's all you have to do is control one LUN. If you take a more complex app, let's say in this case I have Hadoop, right? You might essentially, how would you deploy Hadoop today? You would deploy your data node of Hadoop on one bare metal machine that has 12 disks attached to it. So which means that you have 12 storage LUNs or volumes, right, attached to one unit. Now you're consolidating both of these things, one app with one LUN, one app with 12 LUNs onto the same machine. How do you do noisy neighbor elimination here? So the standard way of doing that would be to say, okay, I'm going to co-cap the max IOP for each and every volume. There's a problem with that, right? The problem here is, in this case, as you have 4 volumes for one app, the green app, and there's 1 volume for Postgres. And you put a boundary around each of these volumes. So which means that at peak, let's say all of them are generating a lot of IO. At peak, you're going to generate the aggregate sum of the max IOPS of all the volumes. But that's not what you want. What you really want is Hadoop should generate no more than, let's say, 50,000 IOPS across any of its volumes, right? So how do you do that? So Robin, because we are application aware, we understand that all these, in this case, the 4 volumes for Hadoop belong to one app, and the max enforcement is happening at that app level, not at the LUN level. And because we do IO scheduling ourselves in the top, we can go and put an envelope around each IO or tag each IO and say that this is the max that it should get. No more than that, right? And it has to be enforced across all these 4 volumes, right? And in this picture, if you see these balls that are coming out, right? They're individual IOs, but all the green, the IOs that are coming for the LUNs that are attached to the green application have this green envelope around it, right? Which is the QoS parameter that you set at an application level. And as far as you know, this is a very unique capability because you're not worried now about LUN level specifics, but you're essentially doing everything again at an application level. And clearly, this is, in order to pull this off, you really need to have IO scheduling done there and done here, but done with the application context in mind. An ability to program your IO schedulers to say that this is the idea of an application, this is the parameters that need to be enforced.
So in the case where you had that distributed database, you'd be setting the IO policy across all of the instances or for each of the instances?
That's a very good question. So let's say you have a 3-partition application. The question you're asking is, do you enforce it across all 3? Now, you could, but we don't. And the reason for that is, if you want to do something like that, you have to have a pretty much very fast interconnect between the machines so that you can exchange the current queue depth, right, across the application. But that degrades the performance of the application, right? So that's why we don't do that. However, because the IOs are tagged with an application ID and they go to the underlying infrastructure with that application ID, you could use that to enforce the priorities here. So if you have multiple applications coming from, or IOs coming from other apps to the same disk, because of the IO ID and the app ID, you could do IO scheduling there. But at the max level, you cannot, because that incurs a performance penalty due to the synchronization that you have.
So when you say you could, you mean that it's in the product now, or it could be?
It is not.
Yeah.
In theory, you could, right?
Yeah.
If you have maybe a very fast InfiniBand RDMA-based kind of an interconnect, maybe that's something that you could think about.
And do you offer monitoring solution where I can prove these values?
Absolutely, yes.
You have?
Yes. So we do monitor at a per LUN level, we monitor at a per instance level, which is one partition of an application, and we also monitor at a per application level. So that is something that we monitor and we also plot. In fact, the demo that Deva is going to show next will show some of those graphs. But there's also a REST API where you can pull this and feed it into any other reporting tool that you want.
So maybe I missed it early on, but how is Robin Systems actually deployed?
Okay, so you have your machines, your standard commodity machines. It is running Linux, Red Hat or CentOS, and then you put our software on that. Once you put our software on that, we do the device discovery, and we spin up a few services, a storage service, an orchestration service, and a networking service. And then as you're adding more nodes, they form a cluster. Once you have a cluster, you can go upload your application, which you call as a manifest, and click on that manifest, and then it just gets programmed. Right? All right. So next one. So this is the solving the noisy neighbor problem in the context of a data-heavy application. All right. So next thing is, if you have your application that's running, and maybe it is you want to run a report, seasonal report, end of quarter report or whatnot, and you want to scale up the resources that it needs. Or rather, you want to increase the resources that it has so that your reports will run faster. So your traditional, or rather a modern day distributed application, the solution to that has always been, if you're running out of juice, why don't you go scale out? Add more units of the same thing so that you can increase the capacity of your cluster. However, that is a very destructive operation, right? Let's say that you want to temporarily run a report and give it more juice, right? If you go down the scale out path where you're adding more instances, you're taking the data, as you're adding more instances, you're redistributing the data that already exists across the new set of nodes also, right? And then maybe your report is done, but then you're stuck with a very big cluster. And then scaling back into smaller clusters, again, very destructive because you have to redistribute the data. So when we thought about this problem, we said, okay, there are several times where you would like to give more juice to your application without necessarily incurring this cost of a very destructive scale out, right? So can we scale up on demand without bringing down the application? So the first thing that you could do, of course, is you can scale up on the compute resources, right? You can scale up on the amount of CPUs that you're giving to it. Straightforward, right? So you can, if you are starved on CPUs, then what Robin can do is it can reallocate some of the running apps so that you will get more CPUs, you're done with your job. But what happens when you're starved on I/O, right? So for I/O, in this picture here, you can see that this application is capped at 20,000 read IOPS, right? So you can go and say, temporarily I'm going to increase this cap, both the write and read, and without, and this is a very key thing, without stopping the application, you are given it more I/O juice. I think you have a demo for this, right? Yes. Right. So that is what you can accomplish, right? Now, once you're done with your report, you can go back and throttle it down to where it was before. No destructive operation, happens in runtime, and you get what you want, right? Okay, so the next thing is, Deva showed you a few cloning use cases, right? One of the lifecycle management features that we have. So you have your, let's say, production Oracle database or production Cassandra database. Let's say you want to clone, right? Or rather, you want to run a report from this database, right? If you were to run that queries on the production database, clearly you're impacting the performance of the production database. So what is the solution that people apply? They clone, right? So one way to clone is to basically make a full copy of your database, call it a test master or whatever, and then run your query there. But as you're making this full copy, your production application is still going to get affected because you're actually moving the blocks out, right? The other way to do that is to do a thin clone, where you keep the data there, but you spin up more compute juice. But even there, you could run a very massive query, let's say a full table scan with a massive join on your clone database, which can again take down the production database. So ideally, what you want to do is you want to have a very fast clone, which is a thin clone. It happens like that in minutes. But at the same time, you don't want to affect the clone queries to affect the production database. So that we can do by giving the cloned application a lesser priority and a smaller max, and ensure that whatever I/O it's generating, let's say it's doing a massive query or a massive join or a full table scan, that will not affect the production database. So this allows you to quickly test reports without really incurring production.
So your use of the term thin clone here is the same as what anyone was using before when we made a thin clone before. So there wasn't cloned data; it was just cloned compute.
Yes. When you say before, like us or other vendors?
No, you.
Okay. Yes.
Yeah.
So in this case, when I say thin clone, your data remains the same, right? You spin up more compute resources, and the cluster is formed and all that. They point back to here.
Yeah.
Now, let's say this cloned copy is making changes. It gets its own write space. So those writes do not apply to the production. So each one gets its own independent write streams, but the unmodified reads are shared across the clone and the production database.
Okay. I'll have to think some more about that, but thank you.